Dear students, welcome to the second lecture on calculus of variation. In the previous lecture, we had discussed the problem. The problem was to find y as a function of x, such that if f is a known function of x, y, and y dot, then the integral between two endpoints s equal to integral 1 to 2 f of x, y, and y dot dx is minimum. This is the basic problem of calculus of variation, and we have found the solution in the form of a differential equation. The solution is delta f by delta y minus d by dx delta f by delta y dot is 0. We had explained that this is known as Euler equation in calculus of variation and Lagrangian equation in mechanics. We shall now use this equation to solve the two problems which were posed earlier in the first lecture. The first was the problem of Brooks-Stockron. The second was the problem of surface of minimum surface of revolution. For that, we want to simplify this equation a little bit. Observe that if f is independent of y, then delta f by delta y would be 0. And therefore, we will get a simplification, that is, delta f by delta y dot would be a constant. And this is a great simplification. But if you recall, in our problem, f was a function of y and y dot. We want to remove y from there. Simple. We interchange the role of x and y. And so, when we had written t is equal to ds by v, we plot the graph, just interchange the role of x and y. We plot x vertically downward and y horizontally. Later on, we will interchange the role again. So in this case, we would now depend on x instead of y. And therefore, our integral will be under root dx square plus dy square over under root 2gx. Which means we can take under root 2g outside. T would be equal to 1 over under root 2g integral of under root 1 plus y dot square over x dx. Now see that in this integral, the function f is now independent of y. And therefore, df by dy dot would be a constant. A simple integration yields that df by dy, delta f by delta y dot is equal to y dot over under root of x, and under root of 1 plus y dot square is a constant. Which means We square it. Y dot square over 1 plus y dot square. This would be proportional to x. We write it as x by c, which means we had chosen our constant to be 1 over under root c. Now, you can solve it either by cross multiplication or by the componendo dividendo method of ratio and proportion. You want y dot square, but in the denominator you do not want 1 plus y dot square, you only want 1. So subtract the numerator from the denominator. So we retain the numerator as it is, y dot square. From the denominator we subtract the numerator. So here we obtain x upon c minus x. You can obtain the same result by cross multiplying. I find this easier. And therefore, y dot is equal to under root of, we take the under root x over c minus x. This now is a simple integral and can be integrated easily. How? Simple. Put x equal to c sine square theta, so that the under root goes. And therefore dx would be equal to twice c sine theta cos theta d theta. Let's put it there, so that y is equal to sine theta over cos theta, and for dx we write 2c sine theta cos theta d theta. And this equals, because cos theta cancel out, we have twice sine square theta. We write it as 1 minus cos 2 theta. So y is equal to c integral 1 minus cos 2 theta d theta. And you can integrate it easily. Y is equal to, when you integrate 1 you get theta, when you integrate cos 2 theta you get sine 2 theta by 2. And therefore we write y is equal to c by 2 theta minus sine 2 theta. We have already made a substitution, x equal to c sine square theta. So we write here x is equal to c by 2 1 minus cos 2 theta. So these are the solutions. Y is equal to c by 2 theta minus sine 2 theta. X is equal to c by 2 1 minus cos 2 theta. Now we can rename our coordinates. We can replace y by x. We can replace x by y, which we had done earlier. Replace our constant c by 2 by a, and 2 theta by simply theta. It's just changing the variables. And therefore we obtain x is equal to a times within bracket theta minus sine theta, and y is equal to a 1 minus cos 2 theta. This is the equation of a cycloid. What is a cycloid? If you roll a disc along a straight line, then any point on the circumference will move like this. This curve is known as cycloid. To see that this is so, let us rewrite this equation. We bring a theta on the left hand. Similarly, here a on the left hand side, square and add. What do we obtain? We obtain x minus a theta whole square plus y minus a whole square would be equal to a square, because sine square theta plus cos square theta is equal to 1. And this is the familiar equation of a circle. What is the center of this circle? The x-coordinate of the center of the circle is a theta. And the y-coordinate of the center is a. We note that whereas y-coordinate of the center remains constant, but x-coordinates of the center moves. As theta increases, the center moves along the x-axis. Therefore, this equation tells you that a circle is moving along the x-axis. And this equation is a cycloid. Now, we have to see what was the time taken should have been the least. Let us actually calculate the time of slide. So, we write down this equation: x equal to a theta minus sine theta, y is equal to a into 1 minus cos theta. Here is the graph of a cycloid. We have to calculate the time taken to slide from this point to the lowest point. But before we do this, we see that theta at this point is equal to pi. Therefore, theta varies from 0 to pi. Let's calculate. Dx would be equal to simply a into 1 minus cos theta d theta. Dy would be equal to the first term will yield nothing, so dy would be equal to a sine theta d theta. And therefore, what is ds? Square the two and add. So that ds will be equal to a under root 1 minus twice cos theta plus cos square theta plus sine square theta, which is again equal to 1 d theta, which is equal to a, you can take 2 common, 2 into 1 minus cos theta d theta. This can be written though as 2a sine theta by 2 d theta, but we need not. And under root 2 gy for the velocity. We substitute. For y we substitute from here, and we obtain under root 2 ga 1 minus cos theta. I said that we need not convert into the second step because this will cancel out. Substitute it in the expression for t. So t is equal to 0 to pi. We had already discussed y is 0 to pi. ds by v. Under root a by g, integral 0 to d theta. It's simple. Integral d theta is equal to pi, so that the time taken is equal to pi under root a by g. Suppose the particle does not start from the origin. It starts from somewhere else. So that particle starts from, velocity would now be equal to under root 2g y minus y0, where y0 is the initial starting point. And we calculate the time which the particle takes to slide down from this point to the lowest point. Everything else will remain the same. But we have now to integrate from theta 0 to pi. And so we substitute for v. 2g, we substitute for y, we substitute for y0 in terms of theta 0. And we obtain 2ga cos theta 0 minus cos theta. Simple. But this we can simplify further, because you know that cos theta is equal to twice cos square theta by 2 minus 1. So we further simplify it in anticipation of later steps. And so our time is ds. Now this we had already calculated, which I had said we can leave it, because in that problem we did not need it. So this 2a sin theta by 2 d theta integral 2ag under root cos square theta 0 by 2 minus cos square theta by 2. And this can be integrated simply because this is dx over under root a square minus x square form, whose integral is sine inverse x by a. So we obtain sine inverse cos theta by 2 whole divided by cos theta 0 by 2 integral theta 0 to pi by 2. I hope you can see that. Nothing involved. I mean, I could place every step, let cos theta be equal to cos theta 0 by 2 multiplied by sine theta by 2. No need. You can see that. Evaluate it and you get pi under root a by g. Remember. Or recall that we obtained the same expression earlier. This expression is independent of theta 0, which means no matter from where the particle starts, it will always take the same time to reach the lowest point. Now that's a very important property, that here is a cycloid. The particle, whether it starts from here, or it starts from here, or it starts from here, it always takes the same time to reach the lowest point. Can you think of an application of this problem? Yes. So this is not only a curve of least time. This is a curve along which the particle always takes the same time. For this reason, this curve is also known as tautochrone. Brachistochrone meant least time. Tautochrone means constant time. Now this has its application, a very important application. If the bob of a pendulum moves along the cycloid instead of a circular arc, then its time period would be independent of the amplitude. Therefore, in the earlier days, what is known as grandfather's clock, there was a pendulum, and at the junction there was a spring in the form of a cycloid, so that the pendulum was actually constrained to move along a cycloid, and therefore the time period was constant, was independent of the amplitude. Whether you push the pendulum this much and it vibrates, or you push it this much and it vibrates, the time period was the same. And that was the most important application of this curve. Now we come to the second problem. I hope you are with me so far. And that's the minimum surface of revolution. This problem was actually added by John Bernoulli, and he had partly solved it, but not with this method. Now we do the same thing here. We change the role of the axis. Why? Because we want our f to be independent of y. So that in the diagram you can see we have marked the y-axis here. We have marked the x-axis this way. So that now the area is 2 pi x ds instead of 2 pi y ds, which we had said earlier. For ds, we substitute as usual dx square plus dy square under the root and replace it by 1 plus y dot square under root dx. So that our function is x 1 plus y dot square. And see that this is independent of y. And therefore, we can apply that simplification which we had done in the previous problem. That delta f by delta y dot must be a constant. This constant we put equal to a. And this is equal to, you differentiate it. Find x remains where it is, and 1 plus y dot square under root. When you differentiate it, you obtain y dot over under root 1 plus y dot square. We apply the same technique of component one division. This implies that y dot square over 1 plus y dot square is equal to a square over x square. And this solves for y dot square either by cross multiplication or by the property of the ratio and proportion, whichever is convenient to you, whichever is easy for you. To me, that ratio proportion method is comparatively easier, so I always do it like that. But you can choose your own. And so we obtain y dot square is equal to a square over x square minus a square. Simplify it again. Take the under root and write dy is equal to a dx over under root x square minus a square. Now integrate it. How? How are you going to integrate it? The best substitution here would be x equal to a cos hyperbolic x. And therefore, this is y is equal to a cos hyperbolic inverse of x by a plus a constant. Reverse this. X is equal to a cos hyperbolic y minus c by a. This curve is known as catenary. Catenary was first discovered by John Bernoulli. That's why I have said he has solved this problem partly. What is a catenary? If you hang a rope between 2 points, between 2 poles, it acquires a curve, a shape. This shape is known as catenary. there is always a sag. I mean, this portion will be known as span. The rope will take this shape. This portion is known as sag. And no matter how tightly you put the rope, there will always be some sag between them. I hope you, I expect you have played badminton. The height of the net at the pole is 5 feet 1 inch. But in the center, it's 5 feet. There is a sag of 1 inch. This shape is known as catenary. In the earlier part of the symmetry, it closely coincides with the parabola, but later it deviates. I think we should stop here. Thank you. Thank you very much.